Hello, everyone. I'm going to talk about electric force, um, also known as the Coulomb force, or also called electrostatic forces. So let's start off right away by looking at the force itself. Um, Actually, the form of the force. So, what if, the system we are describing is two charges, so Q1 and Q2, that are separated by a distance um, that I am going to call R1, 2. And remember that these are labels, they're just labeling the distance between two charges. For a system of two charges, it's not necessary to call it R1, 2, it's enough to just call it R. But just so that we can generalize it later on to multiple charges, I'm going to label it R1, 2. Okay, so this is to be read as 1, 2 and not R12. Um, so they're separated by a distance R1, 2, and we want to know, for example, what is the force that acts on object 2 due to system 1, right? So say, for example, for simplicity, let's assume that they're both positive charges, then we know that they're going to be repelled, and so we know that the forces are going to act away from each other. So this is force 1 acting on 2, or I will abbreviate it as F12. And this is the force of 2 acting on object 1. And they should all have vector symbols because their force is a vector. And I will abbreviate that as F21. Okay, so I have written out what F12 is in symbolic form up here. And so let's look at each of these terms on the right hand side of this equation. So the first thing is Kc. Kc is a constant, right? And its value in SI units is 8.99 times 10 to the 9 Newton meters squared Coulomb to the minus 2. So those are the SI units. You might see this Coulomb force in different forms in different texts. And so, for example, sometimes the constant is not written as Kc. You might see the constant written out instead in this form as 1 pi 4 pi epsilon 0, and epsilon 0 is called the permittivity. These are the two most common forms. There are many other forms of writing this Coulomb force down, and all of them are just differ by what units are used and what constant comes in front. Okay. The next thing is, let's look at each of these terms. So Q1 corresponds to the charge. So what is charge? It's some intrinsic property of the object, and it has a charge. It can be positive or negative, and it has units of coulombs. Okay, so that's written out here. It has units of coulombs. Q1 and Q2 both have coulombs units. Similarly, now let's look at what's down here in the bottom, R12 squared. Okay, so again, this is to be read out as R12, and we're squaring it. R12 is, as I told you already, mentioned already, the distance between the two charges. And finally, there is this funny object on the side over here, which we call R12 hat, because it has a hat on top. And this, every other object in here, in this equation, is a scalar quantity, except for the R12 hat. Okay, R12 hat is a special name. It is called the unit vector. Okay, so what does R12 hat indicate? It has no units, and it only indicates direction. So what it indicates is direction of 2 looking from 1. Okay, so if I am standing on 1 and I'm looking at 2, then what is the direction that I'm looking in, right? So if I'm standing here on 1, and I am trying to look at 2, then the direction I am looking at is in that direction. Okay, so R12 hat represents that. What about R21 hat? Okay, so it's also a unit vector, and by unit vector we mean it has magnitude. It has a magnitude of 1. And when I am standing now on 2 and looking towards 1, then I am going to draw a unit vector that looks like that, right? So this one is R21 hat, and this one up here is R12 hat. Okay. Notice that the same thing doesn't happen for the distance, which is called R12. Okay. And if I were to write R21, the distance doesn't care about whether I started from 2 and moved to 1, whether I start from 2 or move to 1, or whether I start from 1 and move to 2. Okay, this is just the distance. It's a scalar, so it really doesn't care about which direction I start and move in, but the unit vectors certainly do. Okay, and so we will learn how to calculate these unit vectors. Okay, I will show you how to calculate these unit vectors. But before we can do that, okay, so how to calculate unit vectors, because this is important to know how to calculate the forces. But before we can do that, I will go through a brief review on vectors. Okay. So vectors, so how do we define them? There are many ways to define vectors. Probably the easiest definition is something that has both magnitude and direction. So, for example, displacement is a vector, force is a vector, momentum, these are all vectors, and scalars are, for example, energy is a scalar, distance is a scalar, and speed is a scalar. Okay. So these don't indicate any kind of directions, but these indicate both magnitude and direction. Okay. So there are many ways of representing vectors. So first, and I will only go over 2 of them. One is the visual representation. Okay. So when I want to represent a vector, I represent it by a arrow. Okay, where the arrowhead indicates the direction of the vector. And so if I want to now represent it algebraically, I will, there are many ways of doing this, and depending on what text you follow or who you learn this from, everyone does it slightly differently. So I will just quickly go over the possible different ways you might see a vector. But in order to define a vector algebraically, I need to define a coordinate system. Okay, I need to place it in a coordinate system. And so suppose I want to refer to a vector. So for simplicity, let me start off with a vector that starts from the origin and ends up over there. So what is that direction? And so let me label these out also 1, 2, 1, 2, and this is the x coordinate and that's the y coordinate. So I have to define a coordinate system, and you might see this in many different ways, but let me first start with the way that I will use mostly in class, which is I'll write out a vector as a column. Okay, so I can write out this particular vector. Let me call it, let's give it a name, A vector. So A vector is has an x coordinate that is 1, 2, right? That has an x coordinate that's 1, 2, and a y coordinates that's 1 and 2. Right? So I write when I write down a vector in algebraic form, I'm basically writing out the x and y coordinates in algebraic form. So this has I can write this out as 1, 2. Oops, that's not what I wanted to do. 2. So the x coordinate is 2 and the y coordinate is 2. Sometimes you might see this also written out in row format and not in column format. So an alternate way of writing it out is to write it in column form, row format. So that's 2 comma 2. That corresponds to the x and y coordinates. Other ways of writing it out, for example, you might see a vector written out as 2i hat plus 2j hat, where again, as you see, there are these hats on top, and these also refer to unit vectors. Okay, I won't go into details of this notation. Again, an alternate notation is you might see something written out as 2x hat plus 2y hat to represent the x and y coordinates. Okay. So now let's look at what all we can do with these vectors. One of the things that we will do is add them, add or subtract. And so how do I do this visually? So through the visual representation, if I have a vector that looks like this, and another vector, let me use a different color, that looks maybe like that, okay? How do you add these two? Well, if I let me also give them labels. Let me call this a vector and this b vector, and I wanted to add a vector plus b vector. Then what I have to do is start with the toe of a vector. So start with the toe of a vector and move along towards the tip. Then what I'm going to do is I'm going to pick up b vector and move it. So let's move that and move it all the way there to the tip of a vector. So I'm moving the toe of b vector all the way to the tip of a vector without rotating it in any way. Okay, because rotation means you will change the direction and therefore you will change the vector. Okay, so I have moved b vector there, and so I start all the way from the toe of a vector, move to the tip of a vector, then I reach the toe of b vector and move all the way up to b vector. So that's my starting point and that's my ending point. And so let me just move this away. And so the final vector is going to look like that. Okay, and so that's my C vector. Okay, so that's the visual way of doing this, and you actually have to be quite accurate in terms of lengths and angles to get this right, to get it accurately. But usually we'll only be doing schematic diagrams in class. To do this algebraically and to get numbers out, let's see how we can do that. So suppose, for example, a vector looked like this, 2, 1, and b vector looked like this, 1, 3, say for example. Then c vector is a vector plus b vector, which can be written out as 2, 1 plus 1, 3. And all I am doing over here is adding, I'm adding the x components and adding the y components separately. That is, I'm going to add 2 with 1 to get 3, and I'm going to add 1 plus 3 to get 4. Okay, so 2 plus 1 is 3 here, 1 plus 3 is 4. So I get C vector to be 3 and 4. So that was about adding vectors. Now let's come to, now we're equipped to understand unit vectors. So a unit vector is a vector that has only direction and sorry, let me rephrase that, has direction and magnitude of 1. So now that I have a vector, so let's go back to our A vector. What is its magnitude? Okay, so what is the magnitude? In the visual representation, this is straightforward, right? This is simply just the length of this arrow, right? So the length of the arrow corresponds to the magnitude, right? So if I had a large vector, then that would be a long arrow. And if I had a vector that is a small magnitude, then that's just a small arrow. Okay, so the length of the arrow indicates the magnitude. What about in the algebraic form? In the algebraic form, the question is, how do we calculate magnitude? So in order to understand that, let's quickly go back to our coordinate system, and here's our A vector. And so we know that it has a x coordinate that is 2 and a y coordinate that is also 2. Okay, so I can calculate, what I need to do is to calculate the length of this arrow. And so how do I calculate the length? I can use Pythagoras' theorem. So it's 2 units in this direction and another 2 units in that direction. This is a right angle triangle. So the length or magnitude of a vector, which is often denoted like that. And sometimes another abbreviation for this is to just drop the vector. So either one, sometimes we use either of these two. So let me just write like that, which is simply just from Pythagoras' theorem, 2 squared, square root of 2 squared plus 2 squared, which is square root 8. Okay, so we know now what the magnitude looks like. And so a unit vector is basically something that has magnitude 1. Right? So if I had, if I go back and see what r hat was, if I ask you the question, what is the magnitude of r hat? So what is magnitude of r hat? Then that's simply from its how it's defined. R hat is equal to 1. The magnitude of r hat should be 1. Okay. All right. So now let's go back and look at our Coulomb law force again. And over here, we need to be able to figure out how to calculate r hat. Okay. So for example, if I am given, if the location of point 1 is here, and let me just draw a coordinate system. Okay. And location of point 2 is here, then what, for the first thing we need to figure out is what is r12 vector. Okay, that is, if I draw a vector from 1 to 2, what is it? Okay, then in algebraic form I can write that out as I moved 1, 2, 3 units in the x direction and 1, 2 units in the y direction. So therefore, so this is 3 units in the x direction and 2 units in the y direction. So our 1, 2 vector is simply x component 3 and y component 2. Now that I know R12 vector, I need to turn it into a unit vector. Okay, so in order to turn it into a unit vector, I first need to figure out step one is what is the magnitude of R12 vector. Okay, and so let's just go back, and so we have this triangle. So simply the magnitude of R12 vector, which again I'll just abbreviate as R12, which is just the distance, right? And in this case, the distance is simply square root of 3 squared plus 4 squared, plus 2 squared, which is nothing but 9 plus 4, which is square root of 13. Okay, so I have now the magnitude, and therefore, in order to make sure that the magnitude is 1, I can simply calculate R12 hat as R12 vector divided by R12 magnitude. Okay, so how do I do this? What does this mean in terms of the numbers? Well, we know that R12 is simply 1 by square root 13. R12 vector is 3, 2. When I multiply a number by a vector, I just simply multiply this number to each of these components separately, right? So I can write this out now as I'm multiplying 1 by square root 13 with 3. I will get 3 by square root 13 as 3 by square root 13 as the new x coordinate, and 2 by square root 13 as the new y coordinate. All right, the claim is that the magnitude of R12 hat is 1, but can we test that and make sure that it is? So let's see. To calculate the magnitude, all I'm doing is applying Pythagoras' theorem. So it's simply to calculate the magnitude, I have to take the square root of the x component squared plus y component squared, right? So which is 3 squared by square root 13 squared squared plus 2 squared by square root 13 squared, okay, which is 9 by 13 plus 4 by 13, which you can test and see is just 1. Okay, so this is all we're really doing is can be summarized over here. In order to find R12 hat, or the unit vector that tells me the direction, right? It's just telling me the direction of from 1 to 2. Then all I need to do is to calculate R12 vector and then divide it by the magnitude, so I get a unit vector. Okay. Next, I will show you certain problems and how to apply Coulomb's law or the Coulomb force equation to certain situations.